Hello everyone. Let me start with a simple puzzle. When you pull a rubber band slowly, why does it first stretch nicely but then suddenly feels harder to pull? That's exactly the story of today's concept, the stress-strain curve. In the lab, we take a test wire or cylinder and start pulling it with increasing force. We measure the stress, which is force per unit area, and the strain, which is the fractional change in length. Plot these two against each other, and boom! We get the stress-strain curve, a kind of fingerprint of the material. And as you can see in the diagram, the curve begins with a neat straight line, the region where Hooke's law still holds. Now, let's zoom into that first stretch, the author region. Here, stress is directly proportional to strain. In equation form, sigma is proportional to epsilon, or sigma equals E times epsilon, where E is Young's modulus. This portion is linear, perfectly straight, like a disciplined student following rules. The point A marks the end of this linear obedience, and we call it the proportional limit. Within OP, if you stop pulling, the wire happily returns to its original size, no grudges, no memory of being stretched. As the diagram shows, the author line is straight, neat, and reversible. But what happens if we keep pulling past point A? Between A and B, stress and strain are no longer strictly proportional, yet the material is still forgiving. Remove the load, and it snaps back to its original dimensions. At point B, though, we hit the elastic limit, also called the yield point. Beyond this, the material starts to say, enough is enough. The corresponding stress at this point is called the yield strength, sigma y. Engineers love this number. It's the red line they never want their designs to cross. Check the curve in the diagram. The point P is clearly marked, the last safe spot of elasticity. Now comes the drama. From B to D, the wire behaves plastically. Here, even small increases in stress produce large increases in strain. In plain words, the material is permanently deformed, it won't return to its original length. This is the plastic deformation region. At point D, the material reaches its maximum resistance. The stress here is the ultimate tensile strength, sigma u. Beyond this, no matter how carefully you pull, failure is inevitable. In the graph, point D is the peak, the tallest mountain before the downhill slide. What happens after point D? As you keep pulling, the material actually weakens, the cross-sectional area reduces, a phenomenon called necking. Finally, it breaks at point E, the fracture point. If point D and point E are very close, the material breaks suddenly, we call it brittle. Glass is a classic example. If D and E are far apart, the material stretches a lot before breaking, that's ductile. Think of copper wires or aluminum foils, they can stretch and bend without breaking easily. So, the distance between D and E is like a personality test of the material, brittle or ductile. But not all materials sing the same tune. Look at figure 8.3, the stress-strain curve of the aorta, the blood vessel in our body. Its elastic region is huge, it can stretch to several times its original length and still bounce back. Rubber behaves similarly. But notice, their curve is not linear like metals. Hooke's law doesn't hold for most of their stretching journey. Such materials, like rubber and tissues, are called elastomers. They're the superheroes of strain, they can stretch and stretch without snapping. Let's solve a quick problem to see how engineers use this curve. Suppose a steel sample has a yield strength of 2.5 into 10 to the power 8 pascals and an ultimate tensile strength of 4.5 into 10 to the power 8 pascals. If we design with a factor of safety equal to 2, what is the safe stress? Step 1. Write the formula. Safe stress equals yield strength divided by factor of safety. Step 2. Substitute. That's 2.5 into 10 to the power 8 divided by 2. Step 3. Calculate. Result equals 1.25 into 10 to the power 8 pascals. So, engineers would ensure that the material never experiences more than 125 megapascals. And that's how bridges don't collapse under daily loads. Let's wrap up this fascinating journey. The stress-strain curve is the story of a material under load, or A. Linear elasticity obeys Hooke's law. 8b. Elastic limit still reversible. B.D. Plastic region permanent set develops. D. Ultimate tensile strength maximum stress. E. Fracture with ductile or brittle behavior. And for special materials like elastomers, the curve is very different, huge strains but nonlinear behavior. So next time you bend a paper clip, stretch a rubber band, or see a bridge swaying in the wind, remember, you are witnessing stress-strain curves in action. I hope this concept now feels less like a graph in a textbook and more like a living story of how materials fight, bend, and finally break. See you in the next session where we'll explore elastic moduli in detail. Until then, keep pulling, stretching, and questioning. That's how physics comes alive.